In fact, if we've finished chatting, I'll start letting them in now.
Okay.
Yeah, sure.
And the numbers will build up, so I'll start talking to them.
Switch off my video as soon as.
Right, here they all come. Hello, everybody. Nice to see everybody.
Hi, everybody.
And oh yes, we've got all the usual suspects are turning up. Hello. So we've got now I have to keep on pressing the waiting room button because it admits those that are waiting, and then I have to press it again to let some more in. So if I keep on breaking away, that's the reason. I see someone's looking at Aurora. David Edney's got an Aurora in his background. That's good. Right, we've got a nice crowd here. If you don't mind being called a crowd.
No, of course not.
Call us what you like.
It's a Zoom.
as well as Zoom, yes. Right, well, we've got still got a minute or so to go, so I'll just let everyone enter the meeting. Some more to come in.
The Douglas Adams you might have seen there, Olivia, was not the author, but he was the handyman for Heinz Wolff.
Oh, cool.
University, he was his handyman, his technician.
Oh, amazing. That's very cool.
And we've also got another well-known name, that's Stephen King, but I don't know him, but I suspect it's not the novelist.
Hello.
Hi, David.
So how many have we got now? We've got 53. That's pretty good.
As good as an in-person meeting.
I think.
Right, well, it's 1 minute past 8, so that if anybody else turns up, there's one just arrived, let me let them in. Well, I will let them in a minute. Welcome everybody to this meeting of the West of London Astronomical Society. Welcome also to Southwest Herts Astronomical Society members. And I usually say at the beginning of the meetings, if there's any questions you have about astronomy, let us know. But at least you can't wander around and ask us, I'm afraid, on this occasion. But if there is anything, if you're a new member or a recently joined member, then do let someone know that if you've got any questions. And in terms of questions, we will hold them till the end of the main talk. The program is that we've got Olivia Keenan, Dr. Olivia Keenan from Queen Mary University of London. First of all, talking about what I call the missing galaxy mystery. She's got a slightly different title, but it amounts to the same thing. And then after that, David Arditi will talk about what's coming up in the sky in the next month or so, and maybe show us some observations that people have seen. Let me just admit some more people to the meeting. Another 7 to come in. I'll set it to ping when someone comes in. Hold on. And I know there's someone waiting. Okay, a few latecomers. Okay, right, I'm going to start the meeting now. Well, good evening, everybody. And I also already mentioned that Olivia was here. If you could mute yourselves, all the members. In fact, what I'm going to do is to mute everybody, and then I shall unmute Olivia. Otherwise, it won't be much point. So, just doing that. Now let me unmute, or I've asked Olivia to unmute herself. There she is. Right. Okay. Well, as I said a little bit earlier, when people were coming in, we've got Dr. Olivia Keenan of Queen Mary University of London, and she's going to be talking about the mystery of the missing galaxies, or words to that effect. So I'll hand straight over to Olivia.
Fantastic, thank you. Right, I'm just going to share my screen, so bear with me. There's the play button, there we go. Okay, give
Got
me
you.
a
That's
start if that's displaying.
Yep, we've got you. That's fine.
Fantastic, thanks. Yeah, so thanks for having me, everyone. It's nice to be here tonight, beaming to you all the way from Hammersmith, so not too far from you, really. It's quite nice to have not had to drive out in the snow, to be honest, to give a talk. So that's a big benefit of doing it this way. So as Robin said, yeah, this research I'm going to talk about, I did when I was at the University of Cardiff. So as you can see, that's on the screen there. But as Robin said, I'm currently based at Queen Mary University in London. And I work currently for a collaboration that does engagement across the region. So we're working to get a more diverse bunch of people into physics and to reach more people with physics and through stuff like this, really. But yeah, I'll put my researcher hat back on for this evening. I'm going to be talking to you about the missing satellite problem, the missing galaxy problem. It's got a few different names, as Robin said. So where are all the missing galaxies? So first, I kind of want to conceptualize this problem and where it came from. So the two images on your screen, I think I can get a laser pointer on here, actually. There we go. This top one is from a computer simulation. So this fuzzy blob in the middle is meant to be a big galaxy, something akin to our own Milky Way. And all of these little ones around the edge are dwarf galaxies or dwarf galaxy satellites going around the main central galaxy. The bottom image here is of the Andromeda Galaxy. A few of you may well recognize this one. All of these background dots, all the little dots, they're basically all background stars. You can only see a few dwarf galaxies in this. So there's one here, there's one here. I think this may be one. But you can see the kind of obvious difference between these two images is the pure level of dwarf galaxy. So in the top one, we don't have any stars. So the top one is what we call a dark matter only simulation. I'll talk a bit more about dark matter in a minute, but it means there's not going to be any stars in that image. So the core difference here is the number of dwarf galaxies around our main central galaxy. This is something that we see again and again and again. So we see far fewer dwarf galaxies in the universe when we're using techniques than we see through simulation. And the problem's about tenfold. So we're missing about 90% of the dwarf galaxies we think we should see if we understand the underlying physics, which isn't a small problem, let's be honest. Just to sort of take a sidestep and talk about dark matter. So I said the simulation was dark matter only. So what that means is we're simulating these dark matter halos. So every galaxy sits in what we call a dark matter halo. It's kind of a big sphere of dark matter. And we know this because of how the stars in the galaxies move. We know that they move too fast effectively if there weren't this kind of extra mass there. So we know there's something there and we've called it a dark matter halo. So what you're seeing in the simulation here, these kind of blue blobs are dark matter halos, but we don't have any information about the stars and the gas and the dust within that simulation. This is just another kind of way of representing the dwarf galaxy problem. So this is called a Schechter function after the person who came up with it, Schechter. On the left axis here, on the y-axis, we've got the sort of number of objects, number of galaxies. And across the x-axis, we've got, this is luminosity, or it could be mass. They're a proxy to each other. You can see here at the high luminosity, high mass end are predictions in our observed range of galaxies. It's pretty bang on. We don't really have a problem there. So we see the number of big galaxies in the universe we'd expect to see. So we see the number of Milky Way, Andromeda type galaxies that we'd expect to see. When you move to this lower mass end, which is where our dwarf galaxies sit, you can see that those lines diverge quite seriously. And as I mentioned, that's about a tenfold problem. So we observe about 10 times fewer dwarf galaxies than we should based on the physics as we understand it. So I want to talk to you about potential solutions to this, and then the work I've done in kind of exploring some of these and what's happening in the field now. So the first solution is that there could be things called dark galaxies out there. So these are effectively dark matter halos, which won't have any stars in them, so we won't see them through our kind of traditional optical telescopes, but they may well have gas content. So I'm going to talk about that in a minute, how you would go about finding these dark matter halos that don't have any stars but have a bit of hydrogen because it's just so abundant in the universe. The second solution is that all these missing dwarf galaxies are out there, but they're just below our current detection threshold. So as our telescopes get better and better, we'll be able to find more of them. And I'll talk a bit later about the kind of the problems of doing that and the techniques we can come up with to work around it and to help us find faint dwarf galaxies. The other kind of solutions are more on the theoretical side. So the first one is that, as I mentioned, it's a dark matter simulations we're looking at here. It's because of the pure level of computer power it would take to simulate a universe with all the stuff that's actually in the universe. It is absolutely mind-boggling. So we simplify it by just doing dark matter. But because the simulations don't take into effect all of that other stuff, all that baryonic matter, it could be that we're oversimplifying. This doesn't look like it's really a solution. So people have done simulations on a smaller scale, taking more of this baryonic matter into effect, and we don't see the problem go away, but it's certainly something to be aware of. The last point here is the Lambda CDM cosmological model, which is our basic fundamental model of how we think the universe works, like all of our understanding of physics, is flawed. And I'm not going to go into that tonight, but it would be a bit of a problem if it was all wrong. But this is one of the problems which highlights potential discrepancies between our understanding of Lambda CDM cosmology and what we see in the universe. So first I'll talk about dark galaxies. So as I mentioned, when we talk about dark galaxies, we're effectively meaning galaxies with no stars, nothing emitting visible light. And as I mentioned, one of the ways we think we could find these things is for looking for big clouds of hydrogen, because stars and matter all form from hydrogen, the stars form and the hydrogen condenses enough. So there's kind of a couple of scenarios here. Either a galaxy's got hydrogen in it, which has never got to that crucial point of star formation in the first place, so it never got dense enough effectively to do that. Or there's another solution, being that there was an original kind of burst of star formation in the galaxy, but when one of those stars died and went supernova and exploded, it blew away enough gas that there wasn't any subsequent star formation. But there'd still be some gas there that we might be able to detect. So this is an example of what I'm talking about. This is a dark galaxy candidate. It's called Virgo H121 because it's in the Virgo area of the sky, Virgo constellation area of the sky. And it's the hydrogen 21 centimeter line we look at when we're looking for these things with radio telescopes. So that's why it's called that. On the left, you can see it. So all the contours are the outlines of the hydrogen, where we know the hydrogen to be. And the background is an optical stellar image, so you can kind of see it superimposed on the stars in the background. On the right-hand side of the screen here, you can see it in the context of the kind of wider galactic area here. So you've got a galaxy here, you've got another galaxy here, and you've got this object here. So one theory is this object could be something like a dark galaxy. Another theory is you can see here, there's some hydrogen down here, a couple of galaxies. It could be that those galaxies have somehow interacted, thrown some hydrogen off, and what we're seeing is some kind of an off-spin of a hydrogen cloud. We're not entirely sure, and realistically, until we start finding more of these things and studying them more, it's going to be quite difficult for us to be able to say for certain, is this a dark galaxy? Is this a galactic halo with lots of gas in it and no stars, or is it something else? But this is the kind of thing we're looking for. So I'm going to be speaking tonight about the area around this galaxy here. So this is M33, or the Triangulum galaxy. This is just kind of putting it in context of its local environment. So again, we might recognize this person here, this galaxy. This is M31, or the Andromeda galaxy. And M33, it is a giant galaxy, but it's believed to be kind of gravitationally associated with M31, so they're kind of like partner galaxies. And it's also believed that they may well have interacted in the past. So we've observed there's kind of a hydrogen bridge that runs between them. So when they've interacted, their gas has sort of been pulled out in the middle. You can see that a bit more closely on this image here. So the kind of black bits in the background, this is now some hydrogen imagery in hydrogen. So this is Andromeda, this is M33, and you can kind of see this faint blobby stuff in the middle. There's this sort of hydrogen trail there. what you can also see marked on here is all of the satellite galaxies of Andromeda. So I think to date there's 38. There may be a couple of more by now. People keep finding them all the time around Andromeda. And they all look like these examples around the edge. These are 4 of the examples. The sort of typical dwarf galaxy is a elliptical galaxy, so it's effectively a fuzzy blob. It's made up of stars. In colour, in optical colour, it's kind of reddish, yellowish. But they effectively can just look like these stellar overdensities. And we've got a lot of these around the Andromeda galaxy. However, there's currently no dwarf galaxies whatsoever associated solely with M33. There's a couple here you can see which are a bit physically closer to M33 than Andromeda, but based on how they move and how they behave, we can tell that gravitationally they're associated with Andromeda rather than M33. What M33 does have is a few sort of stellar clusters. So again, these are some kind of examples of kind of loose clusters of stars. The core difference between a stellar cluster and a dwarf galaxy, because once you get down to certain size scales, they look pretty similar. This thing on the left looks quite like some of these things. It's basically how the stars move. So it's whether or not they sit in a dark matter halo. One of the definitions of a galaxy is it does sit in this dark matter halo, whereas a cluster of stars, a stellar cluster, doesn't need to. So at the moment, we found some of these sort of stellar clusters around M33, but to date, we haven't found anything that convincingly looks like it's bound together into a galaxy, that its own dwarf galaxy around Andromeda. So this is just another example of what I'm talking about. So how do we identify some of these sort of stellar clusters? So this is a map where all of these black dots are stars, and you effectively can just kind of count them almost. You look at a certain area and there's a higher density of them. So you've identified a sort of stellar cluster in that area. So I'm going to be talking about the hydrogen around M33. As I said earlier, we're looking for dwarf galaxies that don't have any obvious stellar component. So we're looking for clouds of hydrogen that look like they could be rotating in a way that they could be gravitationally bound, that they might be a galaxy. And this is the work kind of previous in the field before I started my work. So this is a map from 2008, produced by the Arecibo telescope. This is part of the Alpha survey, and I also used the Arecibo telescope. On this map, the black here, this is the M33 galaxy in a stellar map of the M33 galaxy. And then these contours here that look a bit like the edge of a fried egg, I think. This is the hydrogen disk. So we've overlaid the contours of the hydrogen disk here. And then all of these sort of coloured in blobs around the edge, these are separate hydrogen clouds. So I believe this was a Grossi et al. Paper in 2008, and I think they found 22 clouds around M33. But lots of them are sort of quite small, and they didn't really explore the possibility of whether they might be dwarf galaxies. So a few years later, we used this instrument, this is Arecibo again, to follow up. So on the left, we've got a picture here of the Arecibo telescope in Puerto Rico in all of its glory. I'm sure a lot of you are familiar with Arecibo. A lot of you, if you've seen GoldenEye, it sinks into the ground. Sadly, it didn't do that in real life. Very sadly to me, and I think, for the radio astronomy community as a whole, the picture on the right shows what happened at Arecibo earlier this year. So this is the observing platform at the top, and that was suspended on wires, and those wires sustained damage over a few different storms and events, and they weren't repaired, and the NSF, through Donald Trump's administration, were underfunding tools like Arecibo, and tragically it led to the platform collapsing into the dish, and you can just see the utter devastation that caused, which is really sad because this was the front-running radio telescope on the Earth for about 50 years. Really was an outstanding instrument, and it's really sad that this is how it ended its days, really. But I was lucky enough to be able to use Arecibo and use Arecibo data, and it was part of the AGES survey, so the Arecibo Galaxy Environment Survey that I worked on, that I use this kind of really awesome telescope. And this is the data cube that we produced from Arecibo. So what you're seeing here, you've got your X and your Y axes here. These are just spatial axes, as you would expect on any kind of map or graph. On your z-axis, your z-axis, what you're actually seeing here is velocity. So you're not seeing how far away something is from us, you're seeing how it's moving in relation to us. And things on this map are coloured in different colours. So the blue here is everything that's at 0 kilometres a second in relation to our Milky Way, which basically means it's moving at the same speed as the Milky Way, which basically means we can't tell whether it's the Milky Way or not. So we kind of have to count it all out. So we've coloured it in blue because to us this is noise. The Milky Way is noise. It's not what we're looking at. We can't tell what it is. So it's blue and it's rubbish. We don't want that. In the middle, this is M33 itself. So you can see it's stretched over quite a range of velocity. It's quite close to us. It's not moving too differently from our galaxy, but it is rotating. So part of it's going to be moving in a more positive way and part of it in a more negative way in relation to where we are. So you see this kind of twisted structure of the galaxy. And then in the back here, you see quite a few of the clouds we found. So these are slightly more negative velocity than the M33 galaxy, but we believe them to be related. And the reason you've got all this red speckle right at the back here, that's the noise. So that noise is actually throughout the data cube. But basically to make it a bit prettier so that you can see M33 in the middle, we've just got rid of all the noise on this visualization. But we've left some at the back to show the kind of level of noise we're playing with and how hard it can be sometimes to pull stuff out of this data and work out what you're looking at. So this is basically a still of the same thing. So as I said, at 0 velocity here, you've got the Milky Way. So yeah, throw away all of that. You've got M33 in the middle, and then you've got some of these clouds that I'll talk about a bit more in a moment, kind of at the back at these kind of more negative velocities. So these are the maps we produced using this. So the one on the left, we've tried to produce a very similar map to the one I showed earlier by Grossi, something quite comparable, so we can see what new stuff we found. We looked for a lot longer over a lot bigger an area, basically with a telescope, which is why we've picked up a lot more stuff than they picked up. In this map, this outline here is the hydrogen disk, so the same as Grossi had, that's kind of hydrogen disk associated with the galaxy. And then each of these big blobs are clouds we found. So we found 11 new clouds that had never been detected before. And we also discovered something else. We discovered that a lot of the clouds discovered by Grossi previously actually are overdensities in the disk of hydrogen around M33. They're not separate clouds. And that's what this image on the right shows. It's a bit confusing to look at. What we've basically done, each color here represents a kind of velocity slice. So say kind of minus 200 kilometers a second through this hydrogen disk as to how the hydrogen is moving in relation to us. And in the same color, we've put dots on for all of the clouds, which we've then discovered are then within that hydrogen disk. So what this basically means is they aren't freestanding clouds, so they wouldn't be a candidate to be dwarf galaxies because they're associated with the disk of hydrogen of M33. You can see that a little bit, I say a little bit better, it's very pixelated. Hydrogen's not high resolution, but you can see a bit more clearly what I mean here. So this is kind of the edge of the hydrogen disk of M33. And this dark bit here is one of these overdensities. So that's something that would have been previously observed as a separate hydrogen cloud. But because we looked for longer, we had the greater sensitivity, we've picked all this stuff up in the middle, which basically shows us that this is an overdensity in the hydrogen disk. It's just a bit of lots of hydrogen, as opposed to being a separate thing from the galaxy. So what that ended up showing us is we could separate these clouds into two populations. So the blue bars here, the blue bars in this bar chart, represent clouds that we now know are connected to the disk of M33, so that can't be separate galaxies. Separately, the black outlined bars here, those are discrete clouds. So they're clouds that are separate, those could be dwarf galaxy candidates, and those are quite interesting. Perhaps kind of unsurprisingly, so this is now velocity with respect to M33, so 0 is moving at exactly the same speed as the galaxy. The blue ones, which we know to be connected to the galaxy, are kind of centered more or less around that. Whereas the ones that aren't connected to the galaxy, some of them are at more differing velocities, but there are also quite a few at a similar velocity, but they're more spatially distinct. This is just to compare the clouds we saw with dwarf galaxies we know, to see if we're looking at a similar population of objects, basically. So on the left-hand side here, all of these red bars are the masses of all of the known local group dwarf galaxies. So the local group is Andromeda, M33, the Milky Way, and all the kind of galaxies around us. It's clustered together in the local group. And this is the masses of all of those plotted on here. And then the thick outlined black bars down the bottom here, these are the masses of all the clouds we found. And as you can see, kind of unsurprisingly, because it's just gas mass, we're not looking at the other mass. As I've said, there's no stars here. They're at the lower end of this kind of mass scale, but they are very much overlapping the population of dwarfs we know about. It's very much a similar population. We're just not getting to the most massive objects, which is what we'd expect. Another demonstration here. So as we've mentioned at the start, all of these predictions are based on cosmological simulations, computer models based on our best understanding of the physics at play here. And one thing we can do with this effectively is we can predict around a big galaxy how many dwarf galaxies of different sizes effectively we'd expect to find. And that distribution that's predicted comes out for M33. If you plug in the numbers for M33, given its mass, given how its velocity moves, all this kind of stuff, the distribution predicted of these blue bars here. And the clouds we found are the black outline bars. So you can see the population of objects we found very, very closely map what we would predict using the simulations, which is really exciting. It shows that we may well be finding a population of objects which are being predicted by the simulations that we're otherwise missing if we just look in the optical data. As I mentioned on the data cube, we found quite a few different clouds, quite a few new clouds, and I just want to focus in on some of these. So this is effectively a slice through the cube. I showed you that kind of 3D thing rotating. This is me just taking a chop through it on one very narrow velocity slice. And in this slice, you can see all of these clouds. So I have separated these out into 9 different clouds because of the detection thresholds we had. So you're looking at how much hydrogen there is over a certain threshold for it to count as a cloud. And once it falls below that threshold, it's a separate cloud. So based on those criteria, these separate in our data currently into separate clouds. However, looking at this, I wouldn't be surprised if this could be followed up, and I know it's something my colleagues are looking at doing with an instrument like the SKA or like FAST in China. This may well be something that we find actually resolves into one cloud, and there's lower density hydrogen there we can pick up with our SIBO. So this is kind of an interesting thing, whether this is actually lots of small clouds or whether this is one quite big cloud, which would then be potentially a dwarf galaxy candidate because it would be quite a big cloud of hydrogen that has been somehow very disturbed through motion or something. So it's kind of blotchy, clumpy in terms of density. This is, in my opinion, the most interesting object we found. This was dubbed by my collaborators as Keenan's ring, and I'll take that. I'll have a gassy ring named after me in space. But this is a new cloud we found. It's big, it's ring shaped. You can see this is a hydrogen intensity map, so the darker bits is where more hydrogen sits. And it's a really interesting object. This cloud, if at the same physical sort of distance as M33, which you think it is actually basically about as big as the galaxy itself on the sky. So it's really big. It's not actually the size of the dwarf galaxies we were looking for. This is the size of a big galaxy. You can also see on the right hand side here, we've got a velocity map, so that shows a bit how the cloud's moving. And this profile we see across here, with sort of a slight change in velocity across it, is quite typical of something like a spiral galaxy. So that's really interesting. When we've searched kind of all the stellar maps of this region, we've looked to follow up, and there are no stars associated with this cloud. This is a really exciting thing we found. This is definitely a candidate for a dark galaxy. Something particularly interesting, as you might have noticed, is this basically hole through the thing. There's a hole in it. We've looked at loads of kind of reasons as to why there might be a hole. So the obvious ones for people who work with galaxies are that something along the lines of a supernova or an active galactic nuclei. So both of those could basically cause an explosion that would blow a lot of the gas out. This hole is effectively 10 times too big to be caused by a supernova and 10 times too small to be formed by an AGN. And also what you'd expect if there had been an explosive event that had driven gas out, you'd expect to see an overdensity of gas sort of around the rim. So you expect to see this kind of dark patterning around here because you'd have this gas build up at the edge of that radius. And you can see we don't see that. Another possibility is that this cloud, this galaxy, whatever it is, has had an interaction with another option in an object in the past. So they've kind of passed through each other, something's come through it, there's a hole in it. We do see not dissimilar things that look a bit like that with holes through them. However, we'd expect to see a lot more kind of gas in the other direction as well. So if you kind of had a flat disk and you pass something through the middle, you'd expect gas to kind of get pulled out and sort of made a mess in kind of that then axes you're moving through. And we don't see that. You know, we can look at the gas, we can look at how it's moving, and it's all very well contained in this narrow disk. There isn't anything in that kind of Z direction as if something's passed through it. So this is a bit of a mystery. I've taken this to kind of multiple conferences to, you know, the world experts in this, and everyone's kind of scratched their heads and said, yeah, it's really interesting, we don't know. So this is very much something to kind of watch out for and watch what we can find out, really. This is just to show you that cloud. Now I've talked about it a bit more in context of the galaxy. So here's the gas disk of M33, and here's this new cloud, and you can see it is really large. Something else you might notice here, we detect this is called Wright's cloud. This was discovered by Mary Wright in the 1970s, I think. This is a big cloud of hydrogen that sits at a similar velocity to this new cloud. There's originally in the literature, it was thought that this cloud could be related somehow to the Magellanic Cloud galaxies and to a gas stream from them coming across the sky. If you look at it, if you look at the data and if you look at the size of this cloud as we know it now to be, it doesn't really make sense. This is quite far away from the Magellanic Clouds, and by the time you get to this point in the sky, the hydrogen associated with them is really, really like tiny bits, and then there's this massive great cloud. Whereas we've now detected this second quite similar object in the same region. So the Magellanic Cloud theory, I think, makes even less sense now. So this is kind of adding to the mystery, is that actually there's two of these big clouds out there, and they don't have stars associated with them, which is really interesting. At this point in my PhD, I submitted a paper with all of this in it. This is a visual representation of the peer review process. I'm sure if anyone who's been involved in it, you know, it can often feel like this. I think this paper was a 13-page paper, and the initial referee's report was 15 pages, so that was good. But we did get here in the end. We got to paper accepted, and this is now published work and published through my thesis as well. So far, the work done with M33, looking for Dart's Galaxy candidates, one candidate found, which doesn't sound too impressive, but actually when you're working in a field that's so new and so evolving, just finding that kind of proof of concept is really key. And it kind of demonstrates we can find objects like this. Now we need to look into them in more depth and really try and understand them. So at the start of my talk, I mentioned that there's multiple kind of possible solutions to this problem. And this is another possible solution. So I kind of switched tacks for a bit in my PhD and looked at a different angle. And this is using optical telescopes, optical data, stuff that looks more like galaxies. But there's kind of a big fundamental problem. So we've got lots of big telescopes. This is a Canada, France, Hawaii telescope in Hawaii, which I use. And they're taking reams and reams and reams of optical survey data. Like we've got to the point in terms of our data capacity storage, in terms of our telescopes, we can take all of this data. And firstly, it's a bit of a problem because we don't physically have the people power to process all this data effectively at the moment, not until we can have trained computers to do it for us. And we've obviously got to tell computers what to look for pretty sensibly because they don't know themselves. But what we also find is something called background confusion. So basically, if you're looking at galaxies in your foreground, if you're looking at a cluster of galaxies, so I looked at the Virgo cluster, it's a big cluster of galaxies, it's getting hard to tell what is a faint dwarf galaxy in the cluster in the foreground and what is a bright background galaxy. And that's what we're calling the confusion limit. So is something big and far away or small and close? And I've got, bear with me a second to change my pointer back. there's a clip here which I think explains this quite well. Now, I've selected to share my sound, but please someone shout at me if you can't hear the sound on this video. So yeah, this is an explanation of what I mean. No, it's not. Give me a second.
Okay, one last time. These are small, but the ones out there are far away. Small, far away.
So that was Father Ted, I think, explaining that far better than I could. It's basically a problem of perspective. So how do we know when we're talking about the pure distances in space and we can't walk outside our window and work out how far away something is so easily? How do we tell if something is small and near us or big and far away? And as I said, I was working on data of the Virgo cluster. So this is a tour of the Virgo cluster. So it's got around 2,000 known members and there's all different types of galaxies in here. And this has been formed, we'll start zooming through now. This has been formed by taking Sloan Digital Sky Survey data and placing all of these galaxies at their relative locations. So we're doing a very Star Wars zoom through of the cluster here. And you can just see the diversity here, right? You can see these really big spiral galaxies, you can see blue galaxies, you can see redder galaxies, you can see ellipticals, you can see really small galaxies, really big galaxies. And there's a big diversity of stuff in here that we're looking at. So before the data I was working on doing this was the state of the art of the Virgo cluster, really. This is a map made by Bengali et al. In 1985. Every one of these little black circles is one of the galaxies in the cluster. So this was kind of the best map we had of where they all sat. And it's got two kind of focal points. So there's big galaxies, basically both of these crosses, which act gravitationally in a way that kind of other galaxies clump around them. So these are the two kind of big central galaxies in the cluster. But the cluster itself extends all the way out here. So it's quite a big thing. It covers 17 megaparsecs of sky. And this is the data I had. So this is from a new survey called the Next Generation Virgo Survey. And the aim was to have data in 5 bands, 5 color bands, and I'll kind of talk a bit more about what those mean and why you would want them in a minute. Due to bad weather, effectively, which happens a lot with observing, the R band stuff more or less had to be dropped. So there isn't, apart from right in the cluster center, there's basically no coverage of the R band. You didn't use the R band. But the other 4 bands that they aim to get, they've got pretty good coverage of, especially like a big chunk of the cluster. So that's fantastic. This is what I mean by bands. So this is wavelength in angstroms, which is, you know, astronomers are the only people who still use angstroms. And this are the filters we use on telescopes. So this is how we split that light up. We put a filter on a telescope, and if we're looking at the Z band, we're only collecting this bit of light. Similarly for the I band, for the R band, etc. And just to make it complicated, we shift where these are slightly based on what telescope we use. So then we have to adjust for it when we're comparing images. The reason this is interesting is, as I showed you on that zoom through of the cluster, you see, optically, you see very different colors looking at galaxies, looking at stars. And if you have this multi-wavelength data, you can get that information out about color. So if you've got more than one of these bands, you can effectively take one away from the other one and see if a galaxy looks more blue or more red. And what that can tell you is something quite fundamental about the galaxy. So here, the blue cloud, the bluer galaxies are star-forming galaxies. They are young and star-forming. They've got lots of gas and dust in them, and they've got young blue stars, and blue stars are big and they burn out quickly. So that's how we know that blue objects, blue galaxies are quite young, because they've got this population of stars that burn out and die quite quickly. They've still got those. Separately, you've then got the red sequence. So this is where your kind of elliptical galaxies sit. These are the kind of the big fuzzy ball galaxies full of very red stars, rusty coloured stars. They're often termed old, red and dead because they're very old objects, they're red in colour, but also there's no new birth, there's no new star formation. So they're effectively stellar relics floating through the universe of kind of gradually aging stars. And in the middle here, we have this green valley. So this is interesting. These are galaxies that don't really fit in here or here, have a mixture of stellar types. And we generally think of this green valley as being a transition. So basically galaxies are young, they form stars for a while, they run out of enough gas to maintain that level of star formation. They transition up here and they end up in this red sequence of old stars that live a lot longer. However, we don't know this. I mean, galaxies obviously live so long compared to us or the entire history of us observing the universe, that we have no way of looking at a blue galaxy, following it for 50 years and seeing if it ends up here. We're not talking about those timescales. So this is something that is generally thought to happen, but there's a lot of competing theories actually that these green valley objects could actually be something very different, and we might not be looking at an evolutionary sequence. So this is why we look at color, and it's quite interesting what it tells you about the stellar populations. So back to the kind of Virgo survey data. As you saw, there were quite big regions and we had 4 bands. We ended up with data on 852 galaxies in 4 bands to play with. And for each galaxy, we had 4 magnitudes, 4 surface brightnesses and 6 colors. That's a lot of data. That becomes a big data problem, especially when you've got one person looking at processing that data, which was me. So it's working out kind of what information you can get from all of that data, and what, as I mentioned, sort of what you can then plug into machines, plug into computers, and what can you get those to do for you. So one thing we did, an issue with this data, once I processed it all, cleaned it all up and measured all of the brightnesses, all of the surface brightnesses, all of the magnitudes and all of the colors. These are these bands. If you take one band away from another, you get a color of all of these galaxies, of 850 galaxies. And you can plot them on a surface brightness magnitude relation. That's what this is. And this is something that's really well observed in galaxy clusters. So basically, partly this is a sanity check. If this line fits my data, I haven't done anything too wrong. And reassuringly, the line fitted the data. We've also got here, we've got a kind of new test sample of new dwarf galaxies, these green points. This is when my supervisor at the time took one of the bands of this telescope, literally just physically looked at the images, looked at the fuzzy blobs, and manually found about 300 new galaxies. Obviously, that takes a while. So we're using that as kind of a training set to see these are the kind of new galaxies we are looking for. How do we separate these from the other stuff in the cluster and from stuff in the background? And I'll talk about the background more in a second. And therefore, how do we tell a computer to do the same thing, so that we're not having people looking through frame by frame by frame of digital images looking for new galaxies, which is impossible. There's too much data and will absolutely drive you mad. So a way of doing this is by also taking lots of images of what we call the background. So as I mentioned, I'm looking at the Virgo cluster. I'm interested in what's in the cluster, but I want to learn how I separate what's in the cluster from what's in the background, from bright things far away and less bright things closer to me. So what we do is we take images of the sky where we know there are no foreground bright galaxies, and this is basically what this is. You're going to pick up all this stuff in the background here, all these galaxies in the background. These are stars. Stars have got these point spread functions, but all of this other stuff is galaxies. You've got a couple of foreground ones here, a couple of ellipticals here, a nice spiral here. Everything else here is your background. So that's what we're interested in. We're interested in comparing the properties of the background to what we're looking at in the foreground. And when you do that, this is what you find. So on this plot, all we've got here is the known cluster dwarfs. So these are dwarf galaxies that we know are in the Virgo cluster. And then this is an off cluster field of background galaxies. And you can see, again, this problem with confusion on here, because once you get down here, once you get to these really faint things, these higher magnitude, these faint galaxies, you can see that if I hadn't colored these differently, because I know they're different objects, it would be absolutely impossible in this region to tell what is a background galaxy and what is a foreground dwarf. There's stuff up here which you can kind of discount, but there's so much here that you couldn't discount that it would be very, very hard to identify new dwarf galaxies. So what my task was to really play around with this data, play around with all of those different measures I have from it. I told you 850 galaxies, 4 magnitudes, 4 surface brightnesses, 6 colors for each galaxy. Just play around all that data and see if there's any way that we can separate all these blue blobs from all the stuff we're really interested in, this cluster data. And long story short, yes, you can. which is fantastic, and I was really pleased with doing the PhD. So what this shows you, here again, you've got all your cluster galaxies. We know these are galaxies in the cluster. Here you've got your background ones. When we plot them like this, they separate really nicely. And that's because we've plotted surface brightness against magnitude. So magnitude is a measure of how bright it is to our eyes. If you could see these things with your eyes in the same way that you can look up in the sky and see Sirius and see Orion and see on a very clear night in the right hemisphere Andromeda, this is how bright they'd be. It's a kind of absolute measure of how bright they look to us. Surface brightness is what we call distance independent. So it's an average measure of the brightness across the surface of a galaxy, broken up by area. But what that means is that if a galaxy is next to me or really, really far away, that surface brightness is independent compared to these galaxies where we can see they're really, really faint, but their surface brightnesses are high. And they have high surface brightnesses because they're actually big, bright objects. They just look faint because they're far away. That's what Father Ted said. Whereas these ones here both look faint to us and are actually faint. They're inherently faint objects. So this is a relationship you can use to separate your background bright galaxies from your foreground dwarfs. And it's something we really hope can help us identify a lot more faint dwarf galaxies by removing this confusion. So, as I mentioned, the purpose of this is to basically train up computers to do this. When you've got your big survey data, you can plop this relationship in, get the computer to spiel through all the data, and then it can just give you the new dwarf galaxy candidates. It can throw away all the guff in the background, and you're not going to be wasting lots of time and energy looking at things by eye, trying to work out if something might be in the foreground or the background. So this is a really, really powerful tool. Now we've got big survey data to find lots of new dwarf galaxies. At this point in this journey, I had to write up a PhD thesis because it turns out when you're funded by a research council, you've got to produce a big book of science at some point. And this just represents what actually happens when people are writing up their theses. I'm sure there's a few people on this call who can relate to this. So that by far the most portion of your time you're thinking about writing your thesis. When it says thinking, I think that's kind. It's probably mostly stressing about writing a thesis or dreading writing your thesis. This chunk here represents all the time you spend fiddling around in LaTeX, Word, whatever your processing software is, trying to make it look really nice. And then this bit here represents actually writing your thesis. Turns out when you buckle down to it, it doesn't take super long to write, but you do want it to look nice and everything. So to kind of summarize what I've been saying about the dwarf galaxy problem, what does this all mean? So are all of the missing dwarf galaxies out there these dark galaxies? Probably not. From what we can see in the field, it's unlikely that they're going to solve this problem that's going to be tenfold more galaxies that are dark galaxies. However, it's likely some are. And if they're a sort of distinct population of objects and they're formed in a different way, that's obviously really core for us to know and core for us to understand. Separately, are they all hiding in the optical data? That's a much more likely scenario. It's likely that an awful lot of them are. There's a lot of papers coming out at the moment finding more and more of these ultra faint galaxies, and they're doing so by using the kind of techniques I've just talked about. So really separating out all the background stuff and looking for these really faint galaxies. So it's likely that this is going to really contribute to the dwarf galaxy problem. Whether or not it's going to solve it is yet to be seen, whether it'll be enough or not, but it's certainly making a big dent in it. So no pun intended, but watch this space.
Olivia, thank you very much. That was a fascinating talk. And knowing our members, I guess there'll be quite a few questions. So at this point, I will try and unmute all the participants. Hold on, or allow them to unmute. It takes longer than you might think. How come I can't access
the technology this year?
Should be three little dots that tell me. Oh, there they are. Right. Allow participants to unmute themselves. That's what we want. Right. Okay. So the procedure is, if you've got a question, could you just wave at the camera? Olivia, if you could unshare your screen, please, and
Yeah,
then I
I will
can
do that.
see the gang. There they are. Right, Lee Spencer has got a question. I saw his hand waving at me. Go ahead, unmute yourself.
Hello, can you hear?
Yep.
Yeah, I can hear you.
Oh, hello there. Just two questions. The first question is, how old is our galaxy? And from a distance, would it look red or blue? The second question is, I know stars are being formed in galaxies as we speak now. Are new galaxies being formed as we speak now? Or were they created at the Big Bang and are just evolving with stars?
That is, so the second part there is really, really interesting. So to answer the first part, our galaxy is about 13.5 billion years old. And I had that vague number in my head, but I did just Google it to double check because we don't always remember these things. It's quite blue. So most spiral galaxies are quite blue in color. They tend to have blue spiral arms. So the stars in the spiral arms are quite blue. And then in the center, they have a bulge, and the stars in that bulge are redder and older. That's because the spiral arms, the way they move, they're more or less density waves. So they move through gas. And as they move through the gas, they compress the gas, and that causes new bursts of star formation. So all of the spiral galaxies we see, including our own Milky Way, are these younger blue type galaxies. And what we're trying to, as I sort of mentioned with that diagram with the red cloud and the blue cloud, what astronomers are really trying to work out is whether the spiral galaxies effectively run out of gas, become all mixed up and transition to look more like ellipticals, or whether they are separate types of galaxy and don't become one another. And that's something we don't actually know. Your question about new galaxies is really interesting. So yes, they are. There are new galaxies being born, but as to what extent, sort of how many they are, that's something we're trying to work out. So the primordial galaxy population was a galaxy population that came out of the expansion of the universe after the Big Bang, and matter sort of clumping and everything condensing, and eventually that forming galaxies and stars, and the structure we see in the universe today. We know that there are new galaxies born, but what we don't know is whether they only exist or they're only born basically where other galaxies interact. And as I mentioned earlier, when galaxies interact, they can spin off bits of gas and all this kind of stuff. And when that happens, you can then get that gas condensing and forming new galaxies, or whether there's any kind of ongoing primordial formation. That's what we're not sure about. So we think that most galaxies born today, it's because of interactions with existing galaxies. But it could be that sort of linked to that ongoing kind of accelerating expansion of the universe we know about, that there's also new stuff being created there.
Okay, any more questions? I think I saw a hand waving. Oh yes, Noel Anderson, yeah. Unmute. There you go.
Thank you, Chair. Evening, Olivia. Noel Anderson, one of the old boys on the team. A very interesting presentation. Can you tell me and enlighten me whether these galaxies are moving with speed or they're slow within the whole hemisphere?
So, I mean, compared to stuff on Earth, they're moving with speed. So the speed of M33 relative to our Milky Way galaxy, it's moving away from us about 300 kilometers every second. But on the scale of the universe, that's not so fast. So because, as I mentioned, we're part of the local group, so that's a group of galaxies, including Andromeda, M33, the Milky Way. They're gravitationally linked together. It's why we kind of call them a group, a cluster. And that basically means that with relation to each other, they're not moving super fast. So in terms of how fast stuff can move in the universe, that's not very fast. But, you know, compared to anything we have daily experience of, 300 kilometers a second is probably quite fast. So
within 6 months, it can be in a different position.
Yes, yeah, they're constantly changing in
relative to the Earth, yeah.
Yeah, but because these structures are so massive, it makes relatively little difference on the timescales we're observing them on. So they are moving, and they're moving by vast distances, because they're so big. They're not really moving in a way that changes how they interact, not over the timescales that, you know, as I said, human lifetime timescale we can follow things on, unfortunately.
Indeed. Okay, thank you, Olivia. Thank you, Robin.
Now more questions. Let's see. Oh yeah, you've got Anurag. Would you like to unmute? Was that you waving, or Well, you are. That's right. Okay, go ahead.
So, how can we see the dark galaxies?
So that's a really, really good question, and actually something I realize now I kind of skimmed over a bit, so I apologize for that. So what we do, we look for the dark galaxies in radio waves. So gas, the hydrogen gas we're looking for, it emits in radio waves, like the stuff that comes out of the radio. And the radio waves that come out of hydrogen gas have a wavelength of 21 centimeters. So if you think of a wave like this, the distance between two of the peaks on that wave is 21 centimeters. And we can look for those radio waves with big radio dishes. So I'm sure you've seen some examples, but I showed the Arecibo telescope that just looks like a big dish. And when we use a big dish like that, we can detect these radio waves, and that can show us where this gas is. And that's how we look for the dark galaxies.
Okay, Paul Skidmore.
Okay, well, thank you very much indeed for an extremely interesting talk, Olivia. I just wanted to clarify a few points. One, at the very beginning, you said that there may be some uncertainty about the validity of lambda CDM. But what I want to establish is, first of all, if that is the case, what modifications or other forms of explanation might be relevant. But in addition, I want to get clearer on CDM in general, because you seem to be suggesting that there might possibly be enough ordinary matter which is maybe obscured by distant galaxies that we can't identify that. Or is it really a combination of ordinary matter and dark matter that may be undetectable at the moment because it's obscured by more distant matter?
Yeah, that's a really interesting one. So, I mean, the big cosmological questions always are. In terms of lambda CDM, it's very, very much the leading model. So when I say there could be flaws of lambda CDM, realistically, it's not what the community think. We think we're more or less bang on with lambda CDM, but there could be some things we don't quite understand. And there's a few problems, and the dwarf galaxy problems, one of them, another one's called the cusp core problem. So it's about how the matter is distributed within galaxies, which don't quite fit with lambda CDM. So as I sort of talked about tonight, what we observe doesn't quite fit with what we predict with our current model. In terms of tweaks to it, the kind of most common one people think about is that C in lambda CDM. So lambda is the cosmological constant. It controls the expansion of the universe, or defines that. And CDM stands for cold dark matter. And basically one tweak to lambda CDM is understanding how cold that cold dark matter is. So it's making sure we've kind of really understood the level of interaction from that. We call it cold because we think it's quite inert, it doesn't self-interact. But it could be that actually it self-interacts a bit more than we expect, and that might be enough, for example, to tweak lambda CDM. But I know there's lots of cosmologists with big computer simulations working on some of those tweaks and seeing if any of them better explain the universe we see. Yeah, your other point was about dark matter and visible matter, and whether we can explain the universe with kind of a less of a dark matter component. At the moment, based on sort of how we see everything moving, so as I mentioned, that's how we know, or what, why we theorize that all galaxies are within dark matter halos. It's because the way that stars move in galaxies, especially towards the edge of a galaxy, is much, much faster than you'd expect if the only sort of main gravitational source was the center of the galaxy. And the only way to explain that is by having this extra distribution of matter that we can't see, that we can't detect, which is why it's called dark, around the edge. And we see that quite consistently across the universe with galaxies, within clusters of galaxies, how galaxies in big clusters move. So sort of right from the small scales of the universe to the big scales of the universe. And it's about 75% of the matter we reckon has to be dark to explain how we see things moving. So it's not, at the moment, certainly, there isn't another explanation that could be given to why stuff moves how it moves, even if there was kind of quite a bit of matter, say in hydrogen, that we weren't observing. It's not going to be enough to explain how everything moves. So I think we still need that dark matter component to those models.
Okay.
Thank you very much. Thank you very much indeed. Good answer. Thank you.
Right, any more questions? Let me look at it. Oh yes, Lee again. Go ahead.
Olivia, I know that you said that new galaxies are being formed, but light travels, according to Einstein's theory, no faster than the speed of light. If a new galaxy is being formed somewhere,
Yeah.
how do we know that it's there? Because if it's formed, if a new galaxy is forming now, either at the edge of the universe where it's expanded, or even within our own galaxy where a star's, say, being born now, we won't see the light from it until it actually reaches us. So galaxies tend to be a bit further away. So how do we know that a new galaxy is being formed?
That's a really good question. And the answer is we don't know live. You're completely right. So one way I think of describing astronomers is a kind of very remote time traveler, because every time we're looking at anything in the universe, we're looking back in time. We're seeing how it was when that light left the object to travel towards the Milky Way, not how it is right now, this second. So to give an example of that, the Andromeda Galaxy, which is our nearest kind of big galaxy cousin, is 2.5 million light years away. So we see the light from Andromeda as it was 2.5 million years ago. So you're completely right. If there's a new dwarf galaxy being formed around Andromeda that we're seeing now, that was formed 2.5 million years ago. And we have no way of knowing if there's anything happening more recently, how long it takes the light to travel.
Okay, thank you.
There's a question on chat from Stephen King. He says, are there CDM only dark galaxies, and would these inform types of CDM slash CDM interactions?
Yeah, that's really interesting. So no, we don't think that cold dark matter is only in the form of dark galaxies. So as I kind of said, every galaxy has a dark matter halo, but similarly, every galaxy cluster or group also sits in a big cloud of dark matter based on, again, how we see things moving and everything. So we're certainly not just looking at those galactic scales. There's dark matter on the huge multi-galaxy scales as well. For the cold dark matter interaction, so one of the defining properties of dark matter, as far as we can tell from looking at how it seems to interact with everything else, is it's non-self interacting. So it doesn't interact with itself. It might combine. So if you two galaxies smash together, their dark matter halos would just kind of form a nice bigger halo. But it's not like when we smash together stars and things get a bit chaotic and they all spin off at different angles. You'd get kind of a coagulation. You wouldn't get an interaction. So yeah, that's kind of, I don't know if that answers the question, but it doesn't interact in the way that normal matter interacts.
Okay. Any further questions now? Oh yes. Okay, Michael.
Yeah, you mentioned that a lot of your work has been done using data from Arecibo.
Yeah.
What impact is going to be the loss of Arecibo for work of this type? Because from what they've said, they're not going to rebuild the facility at all.
No, it was a huge blow, to be honest, because it was basically decommissioned about a year earlier, and that was because of funding through the Trump administration. So we were at least kind of mentally prepared that it was an instrument that was going to go offline, not quite in the catastrophic way it did. A sort of very good thing is, I mentioned a couple of other instruments, but the square kilometre array, which is a multi-telescope array across square kilometres in South Africa, is now online, and that's very, very good for this kind of work, as is FAST, which is a 500-metre dish radio telescope now in China. So Arecibo was 305 metres, and for the last 50 years has been the biggest one. FAST has now come online, and that's bigger. So without those instruments, yeah, we'd have had nothing to do. Arecibo was still a lot of the bread and butter, and certainly until it was decommissioned, it was still running surveys. So the follow-up survey to AGES, which one I was talking about, was one we called WAVES, and there's still lots of data that hasn't yet been processed from WAVES. So there's still new Arecibo data and new science being done on Arecibo data, but unfortunately, there's definitely not going to be any more Arecibo data given the state of the dish. Kind of interesting, I remember about 4 or 5 years ago, as the Trump administration was coming in, Trump was looking at massively defunding blue sky science in the States, and observed countries and organizations had to write cases for their telescopes, and they basically worked out that Trump liked the idea of asteroids because he thought he could mine asteroids for gold. And one of the things Arecibo can do, or could do, is track near-Earth asteroids. So basically the whole science case proposed to the NSF to get a bit more funding, which worked for a few years before the telescope got damaged by storms, was basically saying, we're just going to look at asteroids to find gold. And he was like, yeah, okay, keep the telescope running. So that taught me a bit more about politics and astronomy than I knew previously.
I gather there is a plan that Arecibo may actually be brought back to life. It'll obviously take a lot of money, and I think they're not writing it off completely. So let's keep our fingers crossed. But
Yeah,
certainly
we'll see
won't
what
be
happens with
straight away.
Biden.
It's a big thing to build, isn't it?
Yeah,
Right.
big job to fix now.
Have we got any more questions? I don't see any hands.
Oh, I've got one.
Was that Rachel? I
Hello,
missed.
sorry, it's very dark here.
Yes.
You can't see me. Just a couple of real quickies. Really interested in that large hole in that large and weird hole you were talking about in the near the galaxy. I was going to ask. You've kind of looked at the options of what it could possibly be. And one of my questions is, could it possibly be a black hole? Though they're pretty predictable now. My other quick question was about baryonic matter. I was reading a chart, I don't know, about 10 years ago about, I think it's, if I'm accurate, it's 4% to 5% is matter.
Yeah.
27%, I think, is dark matter, and the rest is dark energy. Is that still accurate in terms of the baryonic chart of the universe?
Yeah, so the first one first, so the kind of hole in the galaxy. So a black hole was something we explored. So the way it could have been formed by a black hole is if that black hole was big enough to be what we call an active galactic nucleus. So it's a super big black hole that when enough matter falls in, explodes. So then that would kind of create that blowing out of the gas. And yeah, there were kind of two reasons we've ruled that out. One, we'd expect the hole to be about 10 times bigger because these AGNs, active galactic nuclei, are only over a certain size scale. And the second one is we just didn't see that density of gas around the edge of that ring that you'd expect to see if you kind of blew lots of gas out. You'd have denser gas. But yeah, it was one of the key things we looked into, whether it could be kind of black hole related. Your other question I've blanked on, remind me.
Baryonic matter. So
Right.
there's 4 to 5% is matter, 27% I think is dark matter, and the rest is dark energy.
Yeah,
is that still accurate?
Yeah, so that's still basically what we think. So that's what comes out against these lambda CDM type models, these cosmological models. It's within that tolerance, as you say. It's sort of 4 to 5%, about 27. So we're not there with like 18 decimal places, but we're pretty sure that it's very much that ballpark. And yeah, 75% is this very mysterious dark energy, which is somehow controlling kind of how everything's moving. And now we know the expansion of the universe is accelerating, but we don't understand what it is and what's causing it.
Thank you.
Okay, any more questions? Let me see. Scan all the faces. No. Okay, well, with that, thanks very much to Olivia for an absolutely brilliant talk. And we've had a few comments. Oh, actually, I have got another one on chat from Stephen King. He says, any mass distribution for Keenan's ring, e.g. from gravitational lensing?
That's an interesting point. I think something that will be, so not for Keenan's ring is the short answer. It's in terms of the size of the universe, it's too close. It's too close for there to be anything big enough passing in between it to cause lensing, which would project it and cause that kind of hole in it. So we know that that's not a cause of that ring shape, but certainly something we'll be looking at in the future is whether we can look for more of these dark galaxies using lensing techniques. So a problem with detecting hydrogen is, as I said, it's radio waves, but they lose their energy quite quickly. So we can only detect them in what we call the local universe. So yeah, our kind of local group of galaxies up to like the next few clusters, but much beyond that, we struggle to detect enough hydrogen to look at this hypothesis. So certainly if we can utilize lensing, we might be able to find hydrogen that's further away and it's being effectively signal boosted by big things in the foreground. So it's certainly an area we're looking into, but no, it doesn't unfortunately explain Keenan's ring.
Okay, right. Well, let me see. I think I don't see any more waving hands. So with that, we really will let Olivia off the hook. Thanks very much indeed, and thanks for coming all the way from Hammersmith to join our meeting. And,
thanks very much for having me. Not dragging me out in the snow.
Yeah, so you can see the virtual applause as well. So with that, thank you, Olivia. And the next item is to hand over to our own David Arditi. If I can find him in the faces here. There he is. Right, I'm going to ask him to oh, he's unmuted already. Yes. And I will just give him the spotlight.
Thank you very much, Robin.
Oh, wrong one. Sorry,
No, that's not me.
No. As soon as I changed it, as soon as I did it, something changed. It's there you go. That's you. Yeah.
Thank you very much, Robin. I think it's quite lucky, actually. We're having a virtual meeting rather than a real meeting tonight, because it might be a bit dangerous to go out tonight. A few years ago, we had a meeting on an icy night, and I came off my bicycle on a bend and slightly injured myself, although I did get to the meeting. So I'm quite glad that we are confined today. That was a very interesting talk, and congratulations to Miss Keenan for getting a ring named after her. A major feature of the cosmos. Now let's try and share the correct screen. Observations and sky notes for this month. I will start with a picture of a piece of equipment. It's always nice to show people's equipment, particularly when they've got homemade things. Douglas Adams has been busy making an adapter between his ZWO camera and a lens, which is a 300mm lens there, which looks a bit military, a bit camouflaged. That's one he uses for bird spotting as well. It's a 300mm f2.8 lens. And he says he's just done this project, and his first image using this setup is this image of the 12-day-old moon. 500 frames taken through moving clouds. Exposure 2 milliseconds. And he can also use this camera with a wide-angle lens. I think it's wide-angle, or a 85mm f2 lens, so that's wide-angle. He says that lens is 40 years old, and he, having made this adapter, can now use any of the old lenses from his collection. And he's got made a bracket arrangement there to attach it to the equatorial mount. And here's his first image taken with that lens. That's set up. This is obviously the Pleiades M45, and that's best 75% of 250 frames with the Pentax 85mm lens. Martin Lewis, as usual, has been doing some stunning planetary imaging, and despite the tiny size of Mars, only 9 seconds diameter on the 15th of January, he's got a lovely image here, beautifully, smoothly processed, showing the Syrtis Major, taken with his big Dobsonian telescope, 444mm or 18.5 inches, and an ASI 224 MC camera, which is a color camera. And here's another image by Martin from 23rd of January. And there you can see the Sinus Meridiani. You can't see any polar cap at all now. The South Polar Cap, which would be at the top of the picture, that's completely disappeared, completely evaporated at this season of the Martian year. And you've got a bit of cloud over the northern end of the planet and the bottom part of the planet. And 3rd of February, looks as if it got bigger, doesn't it? But presumably that's, he's just increased the size. Yes, he's resized that 150%. And for such a tiny object, 7.7 seconds diameter, and they used to say that you could never get resolution higher than about a second with an amateur telescope. But look how much detail you've got there. You can even see the volcano, the big volcano, Olympus Mons there in the lower part of the image. That's just about showing up there. And the upper left, you've got Solis Larcus, the black eye of Mars. A lot of amazing amount of detail on there. Really world-beating image, I think, for such a tiny object, 7 seconds in diameter. And here is a parade of images of Mars showing how it's changed. 17th of November, 27th of December, and the one we've just seen, 3rd of February, all to the same scale. So it's only about a third the size it was in November, and I suppose a quarter of the size it was at maximum in October near opposition. And Martin has gone further than that. He has produced a map of Mars from all his observations this year, or in the 2020 to 21 apparition. So is Martin here on the call? Don't know. I think
yes, I am, yeah.
Do you want to explain how you made this map, Martin?
So that's made from my 6 best images, unwrapped in a program called WinDupos that allows you to take an image, unwrap it and make a segment of a rectangular array. So I ended up with, because I had 6 views from all different aspects of the planet, I could then create a map of segments coarsely stitched together, and then you've got the task of blending it all to make it look seamless. So that's the hard bit, doing that in PaintShop Pro by having a tapered gradient between sections. So it's done with mono images in infrared to get the best contrast and steadiest views. And then I colorized it using the a fake blue color, and then doing an IR synthetic green and synthetic blue blend, and it's worked out actually okay. It looks quite realistic, the coloration, but it's completely fake, the coloration, just based on the infrared.
And you have similar maps for previous apparitions.
Yes, yes.
So you can compare the features and see how they've changed over the years.
Yes. It's quite hard to get good maps of Mars that aren't overly detailed or have got too few details on. So I wanted one that I could use myself. And I've tried to label every single feature that I could see there. And have worked with Richard McKim of the BAA to correctly label as many features as I can on there. So I think he's hopefully going to use it on the BAA site on the Mars section page and add it to the collection of maps that are on there.
Yeah, I think that's fantastically useful, because I found that it is actually difficult to get a useful map of Mars. If you look up maps of Mars on the internet, you get a lot of maps produced by space probes, but they don't show Mars as it looks from Earth. They show the topography, but they don't show the albedo markings as they appear from the distance of the Earth, yes. Which is quite a different thing. Yes. And so a map like this is really useful to amateur astronomers.
There is also a map on the BAA website, which I'm sure you know about, which was produced in the 1920s, which shows an awful lot of detail. And every little feature, all those blobs just to the south of Hellas there, for example, all have got names. And some of them don't appear anywhere else.
Yes.
I had to search for the spelling of one, and the only place I could find was on this map. It's not found on any internet website, no NASA website, and
No.
it was named in about the 1920s, and it's been suddenly revived to name one of these little dark patches in Hellas.
Yeah, that's the Ebisawa map, which is the world standard for nomenclature on for Mars, for the surface of Mars. So Richard McKim always refers to Ebisawa because you look at maps and they'll name different regions the same thing, or the same region will have different names depending on which map you look at. So the Ebisawa map, which is in 3 sections and highly detailed and done from visual observations, which is absolutely incredible, is the world standard, more so than the International Astronomical Union map.
Interesting. So, well, that is really world-beating imaging from Martin there. Moving on from Mars to the Moon, I've had some images from our ambassador in Wales, Rob Davies, in Devil's Bridge near Aberystwyth, and he's been imaging the Moon. This is an image taken January the 23rd with his C9.25 SCT telescope, showing the craters Borealis, Hippalis, and this interesting system of concentric rills right on the terminator, being shown up by the very low angle of illumination. Here's another one, Palus epidemiarum, rather appropriately for the current world situation, I suppose. That is the marsh of epidemics, or marsh of disease in Latin. And it's this dark flat area. And this was again taken with the C9.25, and he's taken 5,000 frames with an ASI camera, monochrome camera, and stacked those up. And here's another one, the Mare Cognitum. He's misspelt it there. It should begin with a C. The Mare Cognitum was named for one of the one of the first, I think it was one of the Russian landers, the first thing that successfully landed on the Moon, landed in this area, and that's why that area was named the Mare Cognitum, the known sea. And here is a very famous crater, Copernicus, and Mare Insularum, which is not a term that's used very much, Mare Insularum, which is the area to the upper right. Copernicus, most famous ray crater on the right, bang in the center of the Moon. We haven't had that much clear sky recently, but I've taken a few more images of Mars, and here's one from January the 23rd, similar view to one of Martin's views, showing the Sinus Meridiani in the center of Mars, which marks approximately marks exactly the 0 of longitude of Mars, and it's that sort of pointed feature sticking downwards towards the north end of the planet, and that's taken with my 14-inch telescope in Edgware. And I've taken a deep sky image. So we've got another galaxy. Heard a lot about galaxies today. Here's a famous one, the Pinwheel Galaxy in Ursa Major. It's very high up in the early mornings at the moment. And I took some exposures with my Celestron 11 Hyperstar system, which is a fast wide field imaging system, f2, 11-inch aperture. And then I discovered I'd imaged this object 4 years ago in 2017 as well, and I'd never done anything with those images, so I decided to combine them all. So I combined, which you can do obviously with galaxies since they don't change very fast. I combined 30 two-minute exposures taken in March 2017 with 28 two-minute exposures taken in January 2021. and that's the combination of all of them. And so you see what kind of a result you can get, even from a very light polluted location, if you use a lot of exposure. So there is nearly 2 hours exposure there, and the individual exposures are quite short. Well, they're 2 minutes, so that's moderately long, I suppose, but they're not very long, because if I did very long, even longer exposures, I would have to guide the telescope, which is a more complicated operation, auto guiding. So I prefer not to do that. And I was able to get away with 2 minute exposures without noticeable drift and just rely on the telescope's sidereal rate tracking. And I've added all those up. And when you add up a large number, like 40 or 50 2 minute exposures, you get very good signal to noise ratio. And I've made a close up version of that picture as well, in case you want to see it in more detail. And there's a few other galaxies in there as well. In the previous one, you can see just at the top, there's some other galaxy and some dwarf galaxy, no doubt. And in the lower right, there's some more. Well, they might be more distant galaxies, following on from the discussion earlier. We don't know if they're associated with this, but I think they are associated. I think they are part of this same group, actually, the Ursa Major group of galaxies. So there's quite a few galaxies in that picture. I haven't identified them all. And you can see the clumps of hydrogen gas in some of the arms there in the star forming regions. From a light polluted location, you can never get a perfect result with these kind of things. There's always light pollution in the background, which I've just suppressed as much as possible. And I always find I get gradients of color in the background, which can't quite completely be suppressed. So I'll move on. The moon is nearly new, so it's a good time, or it would be a good time if we had clear sky, to look at galaxies. And we have a lot of galaxies in the sky in Virgo and Leo, which are high up at the moment, and in Ursa Major, high up later on in the night. February the 19th will be the next first quarter, which will be a very high first quarter moon. February the 27th will be full, and March the 6th will be the next last quarter moon. And here's something slightly interesting. If you want to see a star disappear behind the moon, you can do so on February the 25th at 0240, when a star called Gamma Cancri, or Asellus Borealis, magnitude 4.6, will disappear at the dark limb of the moon. And it will reappear at the bright limb of the moon about exactly an hour later. So that's February the 26th, that 25th, in the early morning, that occultation of a brightish star. The planets, well, the planets are all gone really, apart from Mars, which is still hanging around. They're all the other side of the sun, which must be quite unusual, that the Earth is on one side of the sun and pretty much all the planets are on the other side. Mercury is too close to the sun to see. Venus is the other side of the sun, is almost at superior conjunction. Mars is still visible in the early evenings. It's much fainter than it was, and it's only 7 seconds diameter, but it's higher than it was. And I think that this explains some of the success Martin has been having, even imaging Mars at such small angular diameter, that it's got higher since opposition. So we've got potentially better seeing, but it will soon disappear into the sunset. Jupiter is invisible behind the sun, essentially. It won't come out until late spring in the early mornings. Saturn is also behind the sun. Uranus is still just about in the early evening sky, very close to Mars, in fact, in the sky, visible from sunset, quite high, 48 degrees high in the southwest. And Neptune is now also approaching conjunction and would hardly be visible now. So here's the thing to look out for. February the 17th, the moon will pass Uranus at a distance of 3 degrees, and this shows you where those objects are. The moon and Uranus will be close to the head of Cetus the whale in Aries, and Mars is also just between Aries and Taurus and quite near the Pleiades. And then one day later, the moon will have moved on and it will be close to Mars. It will be 5 degrees from Mars. So that will be an opportunity to see them both in one binocular field. And then in the last few days of February, Mars moves very close to the Pleiades, 3 degrees. So you'll get them in one binocular field. So that might be a nice sight. So the planets are all disappearing, but we do have a minor planet at opposition very soon on the 3rd of March, and it's bright. So you would be able to pick it up easily with binoculars or a small telescope, and it will be there just south of the tail of Leo, between Leo and the bowl of Virgo. And you'd be able to identify it from its slight movement against the stars from night to night. But asteroids, even the biggest and brightest of them, just appear as moving star-like points. This time of year, we usually get this star count, which is run by the Campaign for the Protection of Rural England, and they encourage us all to count the number of stars within the quadrilateral of Orion. And on their website, there's a form for you to fill in, and they use this information. They want you to gather the information between the 6th and 14th of February, and they use this information to construct an accurate current map of the darkness of the sky. In other words, the light pollution across the whole of England. So that is useful information. I came across recently, this is another sort of interface between astronomy and politics. We were discussing in the BAA satellite constellations, and somebody pointed me to this realization you can get on the internet of all the satellites that are over our heads at any one time. And I just thought this was so incredible. I'd never seen it before. I thought I'd show it to you. And you can spin this thing around and you can see, this is in real time, exactly what is over our head. And this is just snowballing with these constellations of tiny satellites, the Starlink satellites being put up by Elon Musk and other companies in the future. This is just filling the sky with this stuff. And you see these little satellites actually look like what they are, and you can point at them and you can find out what they are. Some of them are bits of old rockets from the Apollo era. And look, there's a line of space bee, they're called, going across Eastern Europe. You can identify them all, and so many of them are these Starlinks now, and there's more and more of them. And it's a big issue for both amateur and professional astronomy, that it's becoming very difficult to take surveys of the sky without them being interfered with and potentially ruined by picking up the light of all these objects. And this problem is only going to get worse in the future. So, I'm not sure there's much we can do about it, but maybe amateur and professional astronomers will be able to band together and exert some political pressure. But it's up against huge commercial interests, so I wouldn't hold my breath of any success. But this is something I thought I'd show you.
And a couple of people have asked if you can put the link in the chat when you've gone off the air, and I'll leave it up for a short while to so that people can copy it from the chat.
Okay. And the other thing, yes.
What are the red bits? They look like sort of umbrellas.
The red bits that look like umbrellas.
Well, they're here, just on up on the left top corner. They're like look like kind of
Don't know.
searchlights almost.
Don't know.
Oh, okay.
Mm. The other thing to show you is that Robin has produced a video, and if you've got 8 minutes to spare, last 8 minutes 23 seconds, if you've got 8 minutes to spare, we could show you this video. Oh, I need to give you the sound as well. I just need to make sure you've got the sound, because the sound is an important part of it. And I just choose share sound and then share it again. And there's very relaxing music, and there's no speaking. The music is the Adagietto from Mahler's Fifth Symphony. Here we go. So thank you very much for that, Robin. Clearly, Robin measured the length of the piece of music and made his video exactly the right length.
Yeah, amazing. That was.
And it was made from his garden, I know, because I recognised the trees.
Yes, that's right. It was all made on one night, actually, with the exception of one short sequence. It was all made on one night when it was nearly a full moon. And I thought that would be a good opportunity to try and get some pretty views of the sky and say something about it without that usual commentary.
It was a new moon, presumably, not a full moon.
No, it was a gibbous moon. It was well past first quarter, actually. It's quite high in the sky at the time. That's what made the sky brighter than it would otherwise have been. Otherwise, there'd been little points of light against a black sky, and a bit of moon helps to make the sky show up. It's not all bad.
Oh. Right, well, that's all we have today.
Okay, thank you very much, David. So I will now remove the spotlight from David. There we go. And one thing, I've got a couple of announcements to make.
Mars, and up to the top left of Mars is
something.
Sorry.
That was you, was it, David? Right. Okay.
You started playing your next video. I've stopped it now.
Oh, right. Okay. I've got a couple of announcements to make. So if I just go back to my emails. Now, Astrofest. About this time of year, we start looking forward to Astrofest. In fact, this time last year, it had been, it was the previous weekend. And there were one or two people said, oh, I've heard that there's a virus around and people were being cautious about going into Chinese restaurants. That was about the limit of it. What a lot of changes there have been in the last year. But there is an Astrofest this year as well. And of course, it's going to be online. They don't seem to have got their act together as quickly as we might like. I thought I was bad at organising meetings well in advance, but they have announced their first meeting or their first event, which will be on the 18th of February, which is one of the dates that David mentioned. I think that was the one, 2:30 in the morning, 2:40 in the morning, but it's at 7:30 in the evening, and it's an evening on the Red Planet, and it will be hosted by Lucy Green and Stuart Clark, and there will be a variety of speakers, which they haven't actually specified on their announcement, but they say that at the end of the evening they will go live over to JPL to watch NASA's Perseverance rover land on Jezero crater. Obviously, that will be only seen from the mission control point of view, but it will be quite exciting to see that. We usually get it after the event as a short 10-second clip on TV, but you will be able to see that live on the Astrofest. So I'll put the link to that in the chat afterwards. And there's another event which came through this morning or yesterday. The South Downs Planetarium are doing a star show online, and I think it's going to be free, and it will run between the 12th and the 28th of February. And again, I'll put the link into the chat afterwards. And so that's another event which it sounds as if it's going to be worth looking at. It's called the Dark Night Skies Festival, so that will be available for you to look at as well. Now, I don't know if there are any other announcements. If let me just go back to the Zoom meeting and see everybody. I haven't got any other announcements myself. We will have another meeting in a month's time. It has yet to be fixed. I see David's put the link for the satellite, the satellite animation in the link in the chat there. So have a look at that. I will leave the meeting open for a little while so that people can look at the chat and maybe talk among themselves if they want to on chat or whatever. So,
Robin, if I can give a